All right. So just a reminder, last week we looked at a function and we noticed where it was increasing, decreasing. We noticed the inflection point. We noticed the relative maximum, relative minimum. And we're talking about where it was concave up and concave down. And all of those things we then related to the derivative. Specifically, if y'all look at your notes, when the function was increasing, what was the derivative?
Positive.
Positive. When the function was decreasing, the derivative was negative. Okay. When the function was concave up, we noticed that the second derivative was positive. When the function was concave down, the second derivative was negative. And the transition points were kind of interesting. When that is a relative maximum occurred when obviously the function went from increasing to decreasing, or more interestingly, when the derivative went from positive to negative, so positive slopes to negative slopes. Same thing with the relative min on the function. That occurs when the function goes from decreasing to increasing. But if we're looking at the derivative, that's when the derivative goes from negative to positive. And then the inflection point was a place when the second derivative went from negative to positive or positive to negative. So all kinds of really neat things that we found out about the derivative. And now being able to apply those looks a little bit differently, but we do something called a sign chart. So on the first problem we had like f prime, and we find is something like, let's say that at 3 with the derivative is 0, and we want to find information about the original function. So the way that we find out the information about the original function is we plug in a value over here, like let's say we plug in 2, and when we plug that into the derivative we get a positive value. That tells us that in this region the original function is what? Increasing. And then we pick a value over here to the right of 3, maybe like 5 or something like that. And if it turns out that the derivative is negative, then the function must be decreasing in this range. And you say, well, how do we know it doesn't change from decreasing to increasing any other time? How do you know that it's decreasing all the way over here? And the answer is, if it changed from decreasing to increasing, then this must have gone from negative to positive. And anytime something goes from negative to positive, you've got to pass through
Inflection. The zeros.
You've got to pass through 0. If you go from negative to positive, you've got to pass through 0. And so if you're so the idea is that at the very beginning I said that 3 is the only, I didn't say this, but I implied it. 3 is the only place where the derivative is 0. So anyway, that's sort of the analysis. We'll also do some analysis on the second derivative, where let's say we've got 7. If we say something like where this is positive, plug in like the value of 4, then that would tell us that the original function f is concave up. If we plug in a value over here like 10 to the second derivative, we get negative, and that tells us that the original function is concave down. But we'll do problems like that in a second. But this thing, which is called a sign chart, S-I-G-N, the chart, is the way that we apply all of that information that we talked about before. Okay. So, I think we did 1 or 2 of these. We did 1 and we did 2. Shall we do number 3 together? Sounds good. All right. So they say find the open intervals where the function is increasing and where the function is decreasing. Okay. So that means I'm going to look at the first derivative. So let's go ahead and find the first derivative of this function. When you look at that function rule right there, x squared over 3x plus 6, and I say take the derivative, what comes to your mind? Quotient rule, okay? So maybe we should put a little step-by-step thing in here. Number 1, find derivative. Take derivative. So quotient rule, low d high, so 3x plus 6 times d high, 2x, minus high d low, so x squared. What's the derivative of 3x plus 6, class?
3.
3. All over low squared we go, so 3x plus 6 squared. Let's go ahead and simplify this just a bit. We'll distribute the 2x. So 2x times 3x is 6x squared. 2x times 6 is 12x. And then we have minus 3x squared all over. Denominator, 3x plus 6 squared, that's fine. So here goes. F prime of x equals 6x squared minus 3x squared, so I have 3x squared plus 12x over 3x plus 6 squared. Alright, so I've taken the derivative. In order to figure out where the function is increasing or decreasing, I now need to find out where the derivative is 0. Where are those breakpoints, okay? Although technically, not just where the derivative is 0, but also maybe where the derivative doesn't exist, because that could be a place where we change from increasing to decreasing. So, there is a term for the type of points where the derivative equals 0 or the derivative doesn't exist.
Critical point.
Critical points. So I'm going to put find critical points right here. Find critical points. Notice that is where f prime equals 0 or does not exist. Alright, so this is a rational function. It's a ratio, something over something else. When is a rational function equal to 0?
When the numerator equals 0.
Yeah. This ratio right here equals 0 when the numerator equals 0. So I'm first finding out this part, so I'll say 3x squared plus 12x equals 0. Now I'm starting to pull all my algebra skills in here. I notice anytime this is a quadratic, I could graph this and find the zeros. I could use the quadratic formula, or I could factor it. Let's pull 3x out of both of those. Yep. X plus 4. So that means that either 3x equals 0 or x plus 4 equals 0, which means x equals 0 or x equals -4. Those are two critical points. The other thing I need to figure out is where does the function not exist? Alright? Is there any situation with rational functions where the function doesn't exist?
When it equals 0.
When what equals 0?
The denominator.
When the denominator equals 0. So when 3x plus 6 squared equals 0. I take the square root of both sides, that's just 3x plus 6. Sorry, 3x plus 6 equals 0. Subtract 6 from both sides, I get -6, divide both sides by 3, and I get x equals -1/2. Alright, so those are going to tell me my critical points. Step number 3. Make an f prime sign chart and plug in values to find where f prime is positive and negative. Let me say that again. make an F prime sign chart and plug in values to find where F prime is positive and negative. There's F prime. The values I'm interested in are negative, or the critical points are negative 1/2, 0, and 4. At negative 1/2, the function, the derivative does not exist. At 0, the derivative was 0, and at 4, the derivative was also 0. What we're going to do is we're going to plug in values. We're going to pick a value to the left of negative 1/2. I say, let's make it easy on ourselves, let's just do negative 1.
That's not a negative 4?
It is negative 4, thank you. Yep. Scratch that. Negative 4, negative 1/2, 0.
Quoted as being negative 2.
It might be negative 2. Man, good thing it's, y'all are here. We bring that 6 over here to this side, you get negative 6. Then you divide both sides by 3. 6 divided by 3, negative 6 divided by 3 is negative 2. Thanks. That makes our life even easier. Alright, what else did I do wrong? That's fine. So, what I was saying was we're going to pick a value to the left of negative 4. It could be anything. It could be negative 10, it could be negative 100. I'm going to just pick something easy and say negative 5. We're going to pick another value here between negative 2 and negative 4, so obviously the good candidate would be negative 3. I'm going to pick somebody between negative 2 and 0. Let's say negative 1. And then pick something over here in the positive region to the right of 0. And I say just positive 1 sounds good. Okay. Now, where am I going to plug the negative 5 into? No. I'm plugging it into the derivative, because that's what's going to tell, and if it's positive or negative, then that'll tell me information about the original function. Okay? So, I'm plugging it into this guy right here. Alright? 3x squared plus 12x divided by 3x plus 6 squared. Okay? So, we have 4 of you, and we have 4 as the test data. So, Harley plug in negative 5, Roger negative 3, I have a negative 1, James positive 1, and all I'm interested in is when you plug your value into the derivative, do you get a positive number or a negative number? At this point, what might be the easiest would be to use something like the table. Yeah, I mean, you could plug it into your y equals editor, and then and you could graph it, but yeah, it's possible. So you get good numbers. James, what do you get for 1?
Positive.
I agree. Ivan?
Negative.
I agree. Rigel?
Negative.
Harley? What number did you get?
1.07.
You did do something wrong, but you're correct that it's positive. Yeah, anybody else? Y'all try her value of negative 5. Tell me what you get.
0.18519.
3x squared plus 12x. Yeah, plugging this into your y equals editor is probably the fastest way of getting a good answer on here. So Harley, you should get 0.18519.
Yeah.
Okay. All right, class. Step number 4, I guess, is going to be use that information to find where f is increasing or decreasing. Use that information to figure out where f is increasing or decreasing. So, in this region right here, where the derivative is positive, what is f doing? It's increasing. In this region, it's decreasing. In this region right here, decreasing. And in this region right here, it's increasing. So, the function is increasing from negative infinity all the way up to negative 4, as well as from 0 to infinity. So I'll say union 0 to infinity. It's decreasing from negative 4 to negative 2, union negative 2 to 0. Ivan, how can we check our work?
Do we just look at a graph?
Look
The
at, yes,
original?
but look at which graph?
The original one?
Yeah, let's look at the original function. So I'm going to type in x squared divided by 3x plus 6. So we're going to do, so to check it, we're going to graph this function right here, which is what we're supposed to be telling information about, just to see if we're right. To see, it looks like this. Yeah, James? That's what I've got? Go do a zoom standard on that. Also, let's do y equals. You want to put parentheses around the 3x plus 6. Alright, so with that graph in hand, let's look at this. Class, does it look like the function is increasing from negative infinity up to negative 4? James?
Got him.
Yeah.
I typed it wrong.
Okay.
Just-
Come on. Alright, well then.
Wait, it's that one.
We're doing that one, yep. And there you go. So, does it look like the function is increasing from negative infinity all the way up to negative 4?
Yes.
Yeah, because it's kind of coming along like that. And And then we'll look here, does it also look like it's increasing from 0 to infinity? Yeah, from x equals 0, see it's going up. It's decreasing from -4 to -2, that's when it starts to kind of come down. And then it's also decreasing from -2 to 0. So, our function, it looks like there's an asymptote, right, at -2. So our function kind of comes up and then does this thing, -3, -4, and then is decreasing from -2 to 0, and then it's increasing afterwards. So your function kind of looks something like that, right? Okay, good. I'm gonna cut out some of the homework here for you. Let's go ahead and do an analysis on the sign chart. -4, we said the derivative was 0. -2, we said the derivative does not exist, and it's 0, we said the derivative was 0. Question is, from this information alone, can we figure out where the relative minimum and relative maximum are? The answer is yes. There's a relative max whenever the function goes from increasing to decreasing and the derivative equals 0. So, looking at this sign chart, is there any place where the derivative goes from increasing to decreasing? Where's that?
That's before -4 and after.
Okay, so there's relative max at x equals 4. Why? Because f prime of, sorry, not 4. Because f prime of x goes from positive to negative at that point. And because f prime of -4 equals 0. So you get a relative max at a location where the slope of the tangent line is 0, so you get a horizontal tangent line, and where the derivative goes from positive to negative. Are there any relative minimum based on this information?
Yeah.
Yeah, relative minimum x equals 0, because f prime of x at that location goes from negative to positive. And because f prime of 0 equals 0. What about at -2? Is there a relative max or relative min there? Why not?
Because it goes like, it doesn't turn.
Doesn't cost the 0.
You're all kind of correct, just for different reasons. Y'all are saying over there, Michael Harley's saying, it doesn't change from positive to negative or negative to positive. Absolutely. What's more, Ivan said, the derivative doesn't exist there. So it can't be a relative minimum or relative maximum. And I would say, yes, but it depends on the way in which the derivative doesn't exist. Okay?
Yeah, because it can also be a sharp.
If there was a sharp turn, then it could be a relative min, relative max. Okay? But if the derivative doesn't exist because it's a vertical tangent line or because there's an asymptote, discontinuity, then no way. Okay? So that's going to take care of 4, 5, and 6. 4, 5, and 6 say, look at this and determine where there's relative min, where there's relative max. Okay? We're not going to do number 6, I believe, but we'll do another one of those. All right? So, very quickly, let's go ahead and look at number 4. It says, find the points of relative minimum and relative maximum. Okay? So, to find relative min and relative max, we're going to find the derivative, set equal to 0, do our little sign chart, see where it's positive, where it transitions from positive to negative, negative to positive. So, call it out to me, class. What's the derivative here?
-4x plus 8.
Negative 4x plus 8. Done. Set equal to 0. Pull -8 to both sides, or subtract it from both sides. Divided by -4, we get x equals, I think it's going to be positive 2. Okay? That's the situation where the derivative equals 0. Are there any situations where the derivative does not exist? No. You're not going to run into a does not exist situation on these polynomials. Only on the rational functions. Okay. So this is going to make my life easy. So f prime, I'm interested at 2. So let's pick a value to the left of 2. I say 0. And let's pick a value to the right of 2. I say 10. Let's see if we can do this in our head. Plug in 0. -4 times 0, so that's 0 plus 8. What's this going to be? Positive. Oh, I need to always make it up. This is f prime. That reminds you plugging it into f prime. Let's plug in 10. I like 10 because it makes it easy. So -4 times 10 is -40 plus 8. -2. So negative. Okay. And at 2, we found out that the derivative was 0. So is this a relative max or a relative min?
Relative.
Positive, negative? If you're not sure, just put f right here. We're going from increasing to decreasing. Going from up, da, 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 da. Okay, so yeah, so this is a relative max. So we could say relative max at x equals 2. There's no relative minimum. If I was asking for more justification, you could say because the derivative equals 0 at 2 and the derivative goes from positive to negative at 2. But I'm not asking for a full justification at this point. Just tell me where's relative min, relative max.
So for like relative min, we put like 0 or like none.
You could put none. Relative min, none. Sure. What's your way up? Okay. I'm sure you can do number 5. Number 6 you can skip. Don't worry about that. Just scratch it off. I think number 7. 7, 8, 9 should have come after the next set. Oh, maybe not. Oh no, I did this right. Okay. So number 7 says, for each problem, find the x-coordinate of all the points of inflection and find the open intervals where the function is concave up and concave down. So when we're talking about concavity and inflection points, then I'm more interested in what class?
Second derivative.
Second derivative. Okay? No big deal. Do the derivative twice. So f prime of x, call it out to me.
4x.
Okay. Alright. Don't stop there. Let's do the second derivative. The derivative of the derivative.
4.
It's going to be 4. Oh, you're going to love this. Alright. Let's set that equal to 0, class. 4 equals 0. Wait a second. 4 can't equal 0. So f double prime, there's no location where the second derivative equals 0. The second derivative is always 4. Right? Are there any places where the second derivative doesn't exist? No, it's always 4. Right, yeah, the graph of that graph would look like that. But this is not a graph, this is a sign chart. Okay? So I would normally I'm putting, the x values where this is equal to 0. Well, guess what? It's never equal to 0. Okay? The second derivative is always 4. If I plug, no matter what number I plug in, it's always going to be positive 4. we did not have a situation like this in the previous problems. We always had, the previous problems, we were always able to set it equal to 0, and we found a value, and then we had to plug in all sorts of other guys to figure out what, but this one, there's no breakpoints, there's no critical points, so to speak. It's always positive. The second derivative is always positive. So, what does that tell me? I'm gonna kind of skip a step past the first derivative, go straight to the original function. The original function is always what? Positive, think positive, smile, up like a cup, alright? So, it's concave up. It's concave up everywhere. So, over here I'll write concave up from negative infinity to positive infinity. Wait a second.
They said it's all positive.
What's that?
They said it's all positive, right? Negative.
It's always for even.
I put concave up from negative infinity up to positive infinity. Is that what you're asking?
Yeah.
Because this is the x values from negative infinity all the way to positive infinity for everywhere along the x-axis.
Yeah.
This function is concave up. Okay? Now, this is kind of a spot where we kind of get lost in the middle of stuff because you get calculus and you forget all your basic algebra 2 stuff. Because, I mean, come on now. Look at that function. Is that function concave up or concave down?
Up.
How do you know that?
It's a quadratic positive.
It's a quadratic positive function, yeah. 2 positive. Leading coefficient right there. It's 2. Yeah, of course it's concave up everywhere. But hey, we now have the calculus to prove it. Okay. Concave down anywhere? Nowhere. So if you want to make your homework look exactly like my answer key, you can say concave down, never. My key has an exclamation point. Oh gosh, my son's watching these little television show, little superheroes, little cartoon animated thing, and now he goes like, never! And so we're like, Jake, go make your bed, and he says, never! And we're like, no, that is not acceptable, it's very cute.
That's not the answer.
But that is not the answer I'm looking for here. Okay, are there any points of inflection? That would be a point where the second derivative, the 0 doesn't exist, and we switch concavity. Any of that here?
Mm-mm.
Nah. Okay, we're done with this one. Let's look at a break, if I can. Okay, this one is a little more interesting. So, first derivative, call it out to in class.
3x squared minus 6x.
Okay. Second derivative,
6x minus 6.
6x minus 6. What we want to do is we want to set that equal to 0. Add 6 to both sides, divide both sides by 6, and we get x equals 1. So that's the location where the second derivative equals 0. Are there any locations where the second derivative would not exist?
Mm-mm.
No, that's always, this is good. The only time you get stuff that doesn't exist is when you have a rational function, something over something else to get to 0 in the denominator. Alright, let's draw a sign chart for f dome prime, and we have 1. We know that we've got a 0 right there. And we're going to plug in a value to the left of that. We'll pick something real easy. I say 0. And then plug in a value to the right of that. I say 10. And what are we plugging these values into, James?
The original.
Nope. Not the original function. I've got it listed right here so that we always know. We're plugging it into the second derivative. That's this guy right here. Because we plug it in here to determine whether it's positive or negative. That will tell us whether the original function is concave up, concave down. Okay? 0, let's just do this in our head. 6 times 0 is 0 minus 6. Negative 6, that's negative. let's plug in 10. 6 times 10 minus 6, 4, that is positive. So that tells us that the original function in this region right here is not increasing.
Concave down.
Concave down. You get it?
Yeah.
Because we're doing with the second derivative. Yeah, it's the same sort of analysis. We're looking at whether it's plus or minus, but it tells us different information because we're looking at the second derivative rather than the first derivative. Now, Rigel, that makes me wonder, is Mr. Goddard going to make us do like the first derivative and set it equal to 0 and do all that analysis, figure out where it's increasing, decreasing, and then find the second derivative and figure out where it's concave up and concave down? Like, that would be death. That would be like both of these things all put together, right? Yeah, that sounds like number 10, 11, and 12. Okay, so, alright. And then in this region right here, the function is concave up. Alright, so to summarize this one, we are concave up from 0 to infinity.
I thought it was 1.
Oh, yes, it is 1. Thank you. From 1 to infinity. Concave down from negative infinity to 1. Are there any points of inflection?
Mm-hmm.
Where, Ivan?
X equals 1.
X equals 1. Inflection point, X equals 1.
So the inflection point, that one is 0.
When what is 0?
Is that where the zeros are at?
When the zeros are at on what?
On this sign chart?
On the sign chart of the
Second
second derivative, yes. Inflection point is when the second derivative equals 0 and when the second derivative changes sign, S-I-G-N, from minus to positive or positive to minus. Let me show you something real quick because this is kind of what you're going to do for the homework. The homework, I'm also going to want you to tell me where it's increasing or decreasing. What I was telling Rigel about the perfect storm would be when you have to set this equal to 0, right? In which case then you have to like factor it out, pull up 3x, right? So you have like 3x, then you have x minus 2, which would mean x equals 0 or x equals 2. And then you would do something like 0 and 2, and you would plug in values here, here, and here, and whether it was positive, negative, or positive, that would tell you that whether the function was increasing, decreasing, and increasing. Do you see that?
Mm-hmm.
Okay? Think you could do something like that?
Is that, what did you say it was for 10 or 12?
It's whatever for the, I think it's 10, 11, 12, and 13. Yes, indeed.
So do we just graph those?
Yeah. Wait, yeah, what do you want us to graph? F prime?
Cause
F prime?
there's a graph.
Yeah, no, sketch graph of the function.
So we just graph F of X?
Yeah, whenever you're finished.
Okay.
Okay, I think we've got just enough time to maybe do number 9. Yeah, let's do number 9. So same kind of thing, but we're gonna need to find the second derivative here, okay? So, first derivative, low d high. So 4x plus 8, d high, 2x, minus high, squared, d low, over low squared we go. So 4x plus 8 squared. So that's going to be, distribute the 2, so we have 8x squared plus 16x minus 4x squared all over 4x plus 8 squared. So it's going to be 4x squared plus 16x over 4x plus 8 quantity squared. For the first derivative. Now, let's find the second derivative. Are you ready? Low, so 4x plus 8 squared. D high, what's the derivative of the numerator?
8x plus 16.
Minus high, 4x squared plus 16. D low. Derivative of the denominator is going to be 2 times 4x plus 8 for the first, times
4.
the derivative of the inside. All over low squared we go. 4x plus 8 and 4.
Mr. Goddard, what does it say at the end of the top?
2 times 4x plus 8 times 4. I'm doing the chain rule on this one right here. Okay? Then, thinking this through, and this is a minus symbol right here. We would need to FOIL this out. We would need to FOIL this out. And then you get your numerator. Okay? You can keep this one, but I'll drop the last two on the back. So you can drop 14, 15. Okay? So 9 through 13 are your homework. We talked about first derivative, where it tells you increase and decrease your relative max and relative min. And we talked about the second derivative, where the function is concave up, concave down, and where there's inflection points. Okay? Tomorrow's review day / finish homework day, and then Wednesday's quiz.